Hello everyone, this is Mrs. Lindsay. Today we're going to continue graph theory and we're talking about chapter 7 again. This is in Tannenbaum, the very first part of our book, and regarding networks. Okay, so what is a network? It's a connected graph. It is also weighted, a weighted network in which each edge again is assigned a weight. And in this unit we're going to look at ways of designing efficient networks. And again, that is, we are looking at ways of connecting vertices that use as few resources as possible. Okay, where is this typically used at? Transmitting stations, computer servers, cell phones, people, etc. A lot of people think of a network, especially with computer systems. That's probably the biggest one. But you can use it in internet connections, social connections, wires, cables, roads, etc. Okay, so the edges of the network are typically called links as well. Okay, so this is where it would occur in real life situations, and they can be very expensive to build. So you definitely want to think about minimizing costs, especially again running fiber optic cable lines, rail lines, power lines, again roads, etc. Very expensive, so we want to minimize that. So here's a problem. We're going to go over the problem, and then we're going to talk a little bit more about networks and some algorithms, and then we'll come back to this problem. Sorry, I know this kind of cuts this off sometimes. All right, so an example of a cable network here. Okay, with this cable network, we have, I apologize, go back. All right, so here we have telephone companies contracted to provide telephone, cable, and internet service to these small towns. These towns are located deep in a jungle, which again makes it particularly difficult and expensive. The most practical, environmentally friendly option is to create a network of underground fiber optic cable lines connecting the towns, and it makes sense to build these cable lines along existing roads to make maintenance and repair easier in the future. Okay. So here's an example. They took the weighted graph, took all these cities, so all the vertices A, B, C, E, all the way up through G are the towns, and these are the roads and the weights of each of the links there. Okay. So again, like I just said, vertices are the towns, edges represent the roads or the links. The weight of each edge represents the cost in millions of dollars to create this fiber optic cable connection along that particular road. All right, so the problem that this company faces is utilize the existing network of roads, connects all the towns, and has the least costs. This is known as a minimum network problem. Optical networks. The general theme of this chapter is the problem of finding optical networks connecting a set of points. So again, that means the shortest, cheapest, or fastest, depending upon whether the weight means distance, money, or time. As the last example showed, an optimal network must satisfy certain properties. Properties of an optimal network. 1. Network must be a subgraph of the original graph. Have to use the existing edges, can't draw anything extra in. 2. Network must span the original graph. It must include all the original vertices. 3, it should be minimal. In other words, we want the total weight to be as small as possible. The third requirement implies that a minimal network cannot have any circuits. So again, we cannot have any circuits. If there's a circuit in the graph, we remove an edge without disconnecting it. So, again, imagine that the solid line represents the figure already existing in a minimal network. Would we have to connect X to Y here? And that would be a redundant link. It would make it a circuit, so the answer to that would be no. Trees. All right, what is a tree? It's a network, or in other words, a connected graph with no circuits. That is a tree. A spanning tree is a subgraph excuse me, that connects all the vertices of the network and has no circuits. So again, goes to all the towns, has no circuits. Among all spanning trees of a weighted network, one of least total weight is the minimum spanning tree, MST. So here is an example of a connected network. Minimum spanning tree is drawn in bold. So you can see that this tree, again in bold, is a subgraph or a subset of the original network. Here's another example. So again, spanning tree is in bold there, and again is a subset of the original. All right, so we have 6 graphs coming up on the next few slides here. All have the same set of vertices, A through L. So let's imagine for the purposes of this illustration that these vertices represent computer labs at a university and that the edges are Ethernet connections between the pair of labs. Okay, so in this figure, there is no network. The graph is disconnected, so there's no way to get from the left side to the right side. In this graph, we have several circuits. I'm just going to point out one. Here's one right here, B, C, D, E. Then we have another one over here. We have several of them. So again, this is not, the network is not a tree. In this figure, there's a partial tree connected. Again, we do not have G and I. They're left out. So again, no network. Now we do have one. Figure shows a tree that spans all the vertices. We now have a network connecting all the labs without any redundant connections. So again, this is an example of a network. So hopefully you see the difference between these and the first couple that we have had. Again, the first 3 are not networks. Disconnected circuits, not connected. This is our first one that is a network. All right, so now this tree shows in red. So we've already actually seen this one in blue, but in red, the same tree as in the previous slide, but now highlighted inside of the larger network. In this case, we describe the red tree as a spanning tree of the larger network, which shows a different spanning tree for the same network. So again, in red, we've got a spanning tree. Also, again, here's another one. A different spanning tree showed in red. Okay, so let's talk about properties of trees. In a tree, there is one and only one path joining any 2 vertices. Okay, so if the 2 were different paths joining X and Y, then these 2 paths would form a circuit. So we don't want to connect the blue with the red. That would form a circuit. Okay. So conversely, if there is exactly one path joining any 2 vertices of the graph, then the graph must be a tree. Property 2, in a tree, every edge is a bridge. Conversely, if every edge of a graph is a bridge, then the graph must be a tree. So here is an example. Suppose that some edge, AB, is not a bridge. Then without AB, the graph is still connected, so there must be an alternate path from A to B. This would imply that edge AB is part of a circuit shown. Property 3. Okay. A tree with n vertices has n-1 edges. Okay, and the reverse works as well. If a network has n vertices and n-1 edges, there must be a tree. Thus, all networks with n vertices, a tree is one of the fewest number of edges. Okay, so how do we find this minimum spanning tree? If we have a weighted network, we are interested in finding the most efficient network that connects the original vertices using only existing edges. Again, you can't add anything into the graph. If there are circuits in the graph, then there is also redundancy. So we can delete edges without losing connectivity. Okay, so redundancy. We use that to capital R there. if we talk about the number of edges in the graph and we subtract n minus 1. So m is the number of edges and n is the vertices. This will give us the redundancies. Again, the idea is to add edges starting with the cheapest until we have connected all the vertices. To avoid unnecessary costs, we want to avoid redundancy in the network. That is, we do not want to complete any. Since the new network will be connected and have no circuits, it will be a tree. Since it will use only existing edges, we will use all the original vertices, and it will be a spanning tree. Okay, so how do we do this? We're going to use an algorithm, and I'm not quite sure if I'm pronouncing this correctly. Kruskal's algorithm. It's very, very similar to, if not identical to, the cheapest link algorithm that we learned in the last unit. We'll build the minimum spanning tree one edge at a time, choosing each step the cheapest available edge. The only restriction that we have to our choice is that we should never choose an edge that creates a circuit. So again, cheapest link is really the same thing as this Kruskal's algorithm, okay? And what's really awesome about this, unlike the cheapest link, okay, this is a bit of a difference here. It will always give us the optimal solution. Okay, so what's the procedure? Again, very similar to the cheapest link. Pick the cheapest edge available. If there's a tie, pick one at random and mark the edge used. Pick the next cheapest link and mark it. Continue picking and marking the cheapest until unmarked links available that does not create a circuit. So again, we cannot create a circuit, and we stop when we have n-1 edges selected, which therefore means we have all the vertices selected. So if we go back to our Amazon cable network, okay, we're going to use this algorithm to actually find the minimum spanning tree. What we would do is list out all of the different amounts. So we're going to list out in order from smallest to largest. So looking at here, we would start with 42. It looks like we'd go all the way down until we get down to 74. Okay. So the cheapest one so far is 42. So we'd for sure pick that one. Then the next two would be 45 and 49. So you can see 45 and 49. Then 51, there's where a tie is, but we cannot choose AB because that would create a circuit. So we'd have to choose DG. Next, 53, no problems on that one. The next one after that is 55, but again, this would create a circuit. And then we go to 56, again, creates a circuit. Then we go to 59, and this one we can choose. And that creates our minimum spanning tree. So if you add all those up, $299 million. Okay, so again, this is very similar to the cheapest link. We're going to go through a couple examples. And again, I would have written this all out. I would have, for example, made a list here, 42, then I would have gone 45, 49, and I would have gone through my entire list and crossing ones out that worked. Yep, that one worked, that one worked, that one worked. 51, oops, we had 245, so I would have crossed off one of those. So that type of thing, okay? And we'll do that in our next example. So again, you can refresh your memory on this algorithm, which is, again, identical to the cheapest link. Okay? So again, easy to implement, it's efficient, and it will always give us, always give us the optimal algorithm gives us the minimum spanning tree. So again, let's try some examples here. So the first one, okay? So if we write this guy out, so I'm going to cross these off as I write them down. So I have 1, then I have another 1, then I have 2 and 2, then I have 3 and 3, then I have 4. Do I have another 4? I don't believe so. I do have 2 5s though. And then I have a 6, 7, and a 10. 6, 7, and a 10. Let me change colors here. All right, so if we start with 1, you can see that that one works right over here. It's actually already kind of highlighted. I'm sorry, a couple noises going off here. My other one, yep, that one works as well. Okay. Then we go to 2. Yep, we have 2 options. I can do this one and or this one. So let's see, does that work? I should be able, I believe, pick both of those. So this guy, highlight that a little bit more, and this guy, because that doesn't create a circuit or anything of that nature. So I believe I can pick both of those. Now 3, can we pick 3? Well, let me see here. If I pick this 3 versus this 3, if I pick this 3 versus this 3, I'm not quite sure there is a difference there. So I'll just pick one. I chose to pick the bottom one. We're good, but now I cannot pick this next one because this would make a circuit. It would also work at the reverse. If I happen to choose this one BD, I could not then choose this one. Okay, so let's go over to 4. 4 again would create a circuit. So no. Again, make a circuit. And then we got 5. So this 5 I could not choose, but I could choose this 5. Okay, so are we done? Well, it looks like it. We've hit every vertice. Okay, how many vertices are there? Well, we've got 1, 2, 3, 4, 5, 6, 7. So we should have n minus 1. We should have 6 edges. And do we? 1, 2, 3, 4, 5, 6. We sure do. So we are done. Add all those up. So we chose all of these plus a 5. And that should give us 14. So that's our minimal spanning tree highlighted here in blue. And then we also have the minimum cost or value, whatever that might be, depending upon what these numbers represent, cost or distance, etc. Okay. All right, so try this one. Push pause, see what you come up with, make a list, start out with your list over here. 1, 1. Again, I usually kind of cross those out so I make sure that I don't miss all of these as I'm kind of going through. Create that list, highlight if you need to, redraw it, start over, but again, push play when you're ready to check your answer. Okay, so I got this to be 19. I didn't quite go through all of it. I went through 1, 1, but I wanted to walk through it with you a little bit more. Now, if we pick 2, that should work as well. 3, and we have 2 3s, so it looks like we can pick both of those. Neither of those create a circuit, so I pick both 3s, and then we can go over to 4. And I have 2 4s. Can we pick both of those? And actually we can't. We can pick one of them. I will just choose one. But then if I now go choose this other one, nope, that creates a circuit. Okay. So now let's go over to 5. Will 5 work? Yes, that should work. 6, we have a couple 6s. If I do AB, this one here, nope, that creates a circuit. Okay. This one, nope, creates a circuit. Well, actually, maybe we are done. How do we check this again? Well, how many vertices do we have? 8. Did we hit all 8 of them? Sure looks like it. We should have n minus 1, so in other words, 7 edges. Do we have 7 edges? 1, 2, 3, 4, 5, 6, 7. Sure do. Add those up. Yep, we get that to be 19. Okay. All right, so this concludes Chapter 7 on networks.